This webcast finishes the discussion of Worksheet 2D, where we've been doing some work with velocity versus time graphs. And so we're going to look at the final two questions, numbers 11 and 12. And so in number 11, they give us a motion map, and first they ask us to describe the motion of this object. And so, I want to say that it begins at position 0 meters at time 0 seconds. And then this object moves in the positive direction. I can tell that because the velocity vectors point to the right. It moves at a constant speed of 2 meters per second. And I can tell that because each of these arrows is the same length, and the distance between each of the position points is 2 meters. So it's moving at 2 meters per second. And it does this for 5 seconds. I know that because there are 5 arrows on that motion map. Okay. And then I want to represent that same type of motion with both a position versus time graph and also a velocity versus time graph. And so for the position versus time graph, one way to do that is just to put a dot at the position of the object at each time. So at time 0, it was at 0 meters. At time 1 second, it was at 2 meters. 2 seconds, it was at 4 meters, and so on. Notice that I'm only drawing my line up to a time of 5 seconds because the motion map only gave me 5 seconds of data. Even though my scale on this position versus time graph goes out to 6 seconds, I have to stop at 5 seconds. I don't have information beyond that time. And then, for the velocity versus time graph, well, first of all, I want to label my scale here, but I want, again, to show 5 seconds worth of data, and the velocity was constant. It was 2 meters per second. And so I draw a horizontal line at the value 2 meters per second, and I take that line out until a time of 5 seconds. There are a few questions here. The first asked me to write a physics equation for that position versus time graph. So I used descriptive variables. X means position to a physicist, right? So my position equals the slope, which was 2 meters per second, times t. T represents the variable for elapsed time. And then normally I would put the y-intercept for the initial position, but here the y-intercept was 0, so I can ignore it. Then there's the question of, let's use the position versus time graph to find the displacement from time 1 to time 3. So I can look at the position versus time graph. The final position, in this sense, would be the position at time 3, which was 6 meters. The initial position was the position at time 1 second, which was 2 meters. So 6 minus 2 is 4 meters. Okay, then it says use the velocity versus time graph to find the area from time 1 to time 3 seconds. And so up here on the velocity versus time graph, I did shade that area. And if I want to find the value of this area, I need to take the height times the width. And so we have 2 meters per second, and the box is 2 seconds wide. So 2 meters per second times 2 seconds is 4 meters. And this area represents the displacement for that time period from time 1 second to time 3 seconds. And let's go on to number 12. This, again, is a problem where we're using what we've learned about these graphs to try to solve some problems. So here, instead of giving me a motion map or something, they gave me a table of data. Here is the time, and here's the position at that time. And so to create the position versus time graph, this is similar to what we did in the tumble buggy lab, but I plot the position at each value of time, and I get a graph that looks like this. So I can see it moves in the positive direction for a couple of seconds, it pauses for a second, then it continues. It looks like it's going a little faster in the positive direction for 2 seconds. it pauses for 2 seconds, and then it comes at a very fast speed back in the negative direction. Okay. To create the velocity versus time graph, I have to figure out what is the velocity at each time period. So for the first 2 seconds, I need to find the slope. I see that as it goes over 1 second, it went up 2 meters. So for the first 2 seconds, the velocity was 2 meters per second. Whenever the position versus time graph is horizontal, it's not moving, so the velocity is 0. From time 3 to time 5, as it goes over 1 second, the position changed by 3 meters. So it's moving at 3 meters per second for 2 seconds. Then it paused for 2 seconds, so velocity is 0. And then look here for the last 2 seconds. As the time goes over 1 second, the position goes down by 5 meters. So in other words, the velocity is negative 5 meters per second for those 2 seconds. If we were to draw a motion map, it would look something like this. The object starts at a position of 0. It moves in the positive direction at 2 meters per second for 2 seconds. It pauses for a second, so the dots stack. Then, I'm up at this next level. It moves in the positive direction again at 3 meters per second for 2 seconds, and then it pauses for 2 more seconds, so the dots stack. So now I'm up at this highest level. Then it starts moving back in the negative direction, so my arrows have to go left, and it's moving very fast at 5 meters every second, so these arrows up here have to be 5 meters long. Then we're going to use the velocity versus time graph to find the displacement for a couple of different time periods. First, from time 3 to time 5 seconds. And so I went up here and I shaded that in green. This is from time 3 seconds to time 5 seconds. And so I find this area. It would be 3 meters per second high times 2 seconds. That gives me a displacement during those 2 seconds of 6 meters. And then I did the same thing for the displacement from time 7 to time 9, only that displacement is below the x-axis, right? It's moving in the negative direction. So that area is going to have a negative value because it's negative 5 meters per second, that's the height of the box, times 2 seconds. It's negative 10 meters. To find the average velocity from time 4 to time 8 seconds, I need to find the displacement from time 4 to time 8. So I take the final position at 8 seconds and subtract the initial position at 4 seconds and divide by the elapsed time. The elapsed time from 4 to 8 is 4 seconds. And so the displacement there was negative 2 meters, and that was done in 4 seconds. So the velocity during that time period is negative 0.5 meters per second. And then we wanted to compare that to the speed during that same time period. Well, from time 4 to time 8, the object first is moving in a positive direction, and then it pauses for 2 seconds, and then it moves very quickly back in the negative direction. So I have 3 different parts to that trip, and so my distance, which is what I need to find speed, is going to have the sum of the absolute value of the displacements for each of those 3 parts of the trip. First, it went from 7 meters to 10 meters, so that was a displacement of 3 meters. Then it stayed still, so it wasn't moving, it had a distance of 0 meters for the next couple of seconds, and then it moved from a position of 10 meters back to a position of 5 meters. So the total distance during that third part of the trip was 5 meters. I add those up. The total distance moved during those 4 seconds was 8 meters. 8 meters divided by the 4 seconds is 2 meters per second as the average speed for that